So, hello and welcome back to this 2019 OCR MEI for the maths paper. And so today we're going to be doing section B. Now, section B is going to take up a lot more time. In fact, it is apparently 110 marks. Well, not apparently, it is 110 marks, which is about triple the amount of marks of section A. So we might need to split this into a few more parts of one, because it's going to take a while, and obviously I don't want massive recording files saved on my computer. So we'll just rip the band-aid off, get straight into this. Question 8 is going to be a roots of polynomials question, it would seem, which is always cool, I guess. I'm not the biggest fan of these, I can't lie, but they're obviously always going to come up. So yeah, so the roots are alpha, 1 over alpha, and beta. And the first question is a 6 marker, and it says evaluate in exact form the roots of the equation. So we are obviously going to start off with the some of the singles, some of the doubles, and some of the triples. If you don't know what I mean by that, we basically can say that alpha plus 1 over alpha plus beta, which is the sum of each individual root, is actually going to be equal to the coefficient of this x squared term here, the negative coefficient of the x squared term, over the coefficient of the x cubed term, or minus b over a. You might see it more commonly written out. So basically the coefficient of the second term in the polynomial over the coefficient of the first term in the polynomial with a negative sign. So that's going to be minus 1 over 1, but then minus that, so it's just equal to 1. So alpha plus 1 over alpha plus beta is going to be equal to 1. And hopefully we can get some simultaneous equations here. So we have one equation which is got alphas and betas in. We can simplify that out later, but we want to obviously get a second expression because we have two unknowns here. So we don't actually want to use factor theorem here, if you guys are thinking that, because we have that k. So yeah, the other one of these coefficients we know is the coefficient of the constant. So if that's minus b over a, that'll be c over a, so that'll be minus d over a. So we can say that that'll be the sum of the singles, sum of the doubles, and that'll be the triples. So that would be alpha times 1 over alpha times beta is going to be equal to minus 2 over 1. So we get that alpha times 1 over alpha is obviously just 1. So we get beta is actually just equal to 2, which works out quite nicely there. Now we can sub that into our original equation. So alpha plus 1 over alpha plus 2 equals 1. And then from here, you then multiply both sides by alpha. Be careful here not to forget to multiply one. So this actually becomes a constant, since 1 over alpha times alpha is 1. And then plus 2 alpha equals alpha. And then alpha squared. And then we're going to put plus alpha plus 1 equals 0. This looks like it's going to be complex, I think. So we will complete the square. You could complete the square. I'm actually going to put this into my calculator, which I think you should always do. You should always put these into your calculator just so you don't make, a mistake, because this will really only be like maybe one method mark at most. So here we get alpha equals minus 1 plus or minus root 3i, and this will be over 2, and this will be over 2. Make sure you separate your fractions there, because that could lose a mark, because you need to show separately that this is the real part, this is the imaginary part. And this makes sense, because one is the complex conjugate of the other, so that means that one is a reciprocal of the other. Because that's the definition of complex conjugate, right? It's the number used to rationalize a third of that like complex number. So that checks out. So we could say that alpha equals minus a half plus root 3 over 2i, and then alpha to the minus 1, or 1 over alpha I should probably put. 1 over alpha equals minus a half minus root 3 over 2i. Now I don't think it matters which order you put them in, because either one would work, and you can't really determine which one is alpha and which one's 1 over alpha, but yeah, so that would be our answer to the roots of this polynomial. So 8b will be to find k, and so now we can just use factor theorem here. So this is just your A-level recap. So there's lots of ways you could do this, but I'm just going to use factor theorem since I feel like that's the simplest way to do this. So 8 minus 4 plus 4k, and then minus 2. Sorry, that is 2k. Yeah, 2k equals 0. So that's going to be 4 minus 2, 2 plus 2k equals 0. And then so k equals minus 1. Let me just check that works out. So 4 minus 2 minus 2, yeah, okay. So I'm going to be doubling over this recording. I'll be doing the proof by induction question since I lost the audio for it. I genuinely don't know where it is. But anyway, so the base case is 5 to the 1 plus 2 times 11 to the 1, since we are going to go for n equals 1. And that gives us 27, which is divisible by 3, so therefore true for the base case, basically. So yep. And then next we would be doing the assumptive step, which is assume that it's true for n equals k, sorry, so 5 to the k plus 2 times 11 to the k equals 3m, where m is just some sort of integer, positive integer. So then I was going to put there for all m positive integers, but we can deal with all that stuff later on at the end of the question. So yeah, obviously then you've got your inductive step, which is going to be 5 to the k plus 1 plus 2 times 11 to the k plus 1, and you want to somehow get that into a form where we have that being divisible by 3. So what we want is 5 to the k plus 2 times 11 to the k realistically, since we know that that is divisible by 3. So if we can get it in the form like that, like I've written there, then we can show that the entire expression is divisible by 3. So for this, what I did was I said, okay, well, I'm just rubbing stuff out here. It should show in a second what I did. Yeah, so we can let 5 to the k equal so yeah, we can rewrite this as 5 times 5 to the k plus 2 times 11 times 11 to the k, and then from that we can say that 5 to the k is equal to x, and we can say that 11 to the k equals y, and 2 times 11 to the k, sorry, equals y, and I'll just explain why that is. That's basically because what we want to do here is we want to basically get an expression for x and y. x plus y, sorry, since that we know is a multiple of 3. So if we write this as 5x plus 11y, we can see a way to easily get out x plus y, sort of by completing the square. If you see here, I've got an x plus y and then added on a constant at the end to make it equal to the original expression. And this allows us to put it in the form of 5 brackets x plus y plus 6y, which obviously we know x plus y is equal to 5 plus 2 times 11 to the k, which we know is a multiple of 3. So then we have 5 times 3m plus 6y is equal to our original thing that we had from the inductive step, and we can factorize out a 3 from that. So since we can factorize out a 3, we can say that that entire expression is a multiple of 3. And yeah, so the real trick there was you want x plus y, since you know x plus y is a multiple of 3, so you want to manipulate the algebra any way you can to get x plus y. And in this case, it just so happened to be sort of completing the square on this sort of equation here. And by that I mean like factoring something out and then adding on a term to make it equal. So then you just want to write your like inductive statement, if that makes sense. So since the 3 can be factored out, this expression must be divisible by 3. So then this is what you want for all induction questions. Basically you want to be saying, I think I'm going to write in a sec, if true for n equal k, then true for n equals k plus 1, and true for n equals k plus 1. If true for n equals k, true for n equals k plus 1. Since true for n equals 1, true for all n elements of the positive integers. And so yeah, that's how you would approach that question. It's a pretty tricky one. I'm sorry if the commentation is a bit confusing. It's just because I lost that original audio, so I can't really exactly replicate what my thought process was at the time. But I tried to give a good description of what I was doing. But yeah. Right, so now with question 10 here. In this question, you must show detailed reasoning. You're given that minus 1 plus I is root of the equation. Oh, sorry. Z cubed is a plus bi, where a and b are real numbers. Find a and b. So if z cubed equals a plus bi, then minus 1 plus I cubed is a plus bi, since this is the value that makes this equation 0. And so then we can choose binomials, so minus 1 cubed plus I squared minus 1, no sorry, other way around, minus 1 squared I, and then plus minus 1 I squared, then plus I cubed. So this is going to give us minus 1 plus minus 1 squared is, oh wait, I forgot my Pascal's triangle almost there. That could have ended very bad, so remember Pascal's triangle needs to be coefficients of 3 there. So this is going to be plus 3i, and then minus 1 times minus 1 is 1, plus 3, plus I, oh wait, sorry, minus I, and then you'll get this is equal to 2 plus 2i. So let me just double check that because I made quite a few mistakes there. Minus 1 cubed minus 1. 1 times I is I, 3i. Minus 1 times minus 1 is positive 1. So it's just 3 minus I. Yeah, okay, that seems right. So yeah. Oh yeah, so I want A and B, so A equals 2, B equals 2. Right. 10b. Find all the roots of the equation pi, giving your answers in the form r I e to the I theta, where r and theta are exact. So z cubed equals 2 plus 2i. So then z equals 2 plus 2i to the third. So now I want this in exponential form. So let's calculate the modulus. So that's going to be root 2 squared plus 2 squared, 2 root 2, which, and then cube rooted is root 2, but we'll put 2 root 2 to the third, and we'll also put, we got that by 2 squared plus 2 squared to the half equals 2 root 2, just because it's a detailed reasoning. And then let's also draw a triangle here actually, just so we make sure we get the detailed reason marks. 2, 2. This will be arctan of 1, which is equal to pi over 4. So it's going to be cos, oh wait, wrong line. Root 2, so it's going to be cos pi over 4 plus I sine pi over 4 to the 1/3. And then this is kind of badly laid. I kind of badly laid this out, I can't lie, but z equals root 2 and then cos pi over 12 plus I sine pi over 12. I don't know why I put this in mod arg, because it wants it in exponential, so equals root 2 e to the I pi over 12. And I'm pretty sure that gives us a new solution. Root 2 e to the I pi over 12. So that's one of our solutions there. And then z2 will give us root 2 e to the I pi over 12 plus 2 pi over 3. Which equals root 2 e to the I e to the I 3 pi over 4. Let's check that. Pi over 12 plus 2 pi over 3. Yeah, 3 pi over 4, which is e to the I 3 pi over 4. So that's going to be a solution we already had. Right? Yeah, it is. So we want to ignore that one. And then, so Z3 is going to be our solution that we want, which is going to be root 2 e to the I, and then, well, we've got 3 pi over 12, which is, this is not 3, this is 9 plus 2 pi over 2 times 4, which is 8 pi over 12, which is equal to 17 pi over 12. So this is root 2 e to the I 17 pi over 12, which is, these are our two values we want. So those are all the roots of the equation. Right, next question. Chris says the complex roots of a polynomial equation come in complex conjugate pairs. Explain why this does not apply to the polynomial equation in part A. Well, that is quite strange. Chris says complex roots of a polynomial equation come in complex conjugate pairs. So if I had like z equals minus 2, then I would get z squared equals minus 2, then I see, because it's a cubic. Wait, No, but even if it is a cubic, it should then only have a one pair of complex roots and then one real root. Well, I feel like the equation in A isn't strictly a polynomial, is it? Because a polynomial is only defined for real coefficients of its values, and those are complex coefficients. So I even think the equation, correct me if I'm wrong, but I swear the equation in A doesn't even count as a polynomial, and that would be the answer I would give, but it says that it is a polynomial, so I'm going to leave that one for now, and I'll come back to it later. So 11a, specify fully the transformations represented by the following matrices. So we have m1 equals that, I'm not going to write it down, and then m2 is that. So I feel like m1 is definitely going to be a rotation. Let's do cos minus, what's going on with that? Cos minus 1 of, why am I in degrees? What? Okay, cos minus 1 of 3/5 is going to give me 0.92, and then let's just check the sine minus 1 of 4. Oh, wait, yeah, no, this is a Pythagorean triple. Yeah, it's definitely a rotation. A rotation, and then it should have been degrees actually, yeah, because this is a rotation. Cos minus 3/5. Yeah, because that's cos theta. Cos theta equals that, yeah. Rotation 53.1 degrees. Anti-clockwise. Anti-clockwise? Yeah, anti-clockwise. Rotation. Anti-clockwise, yeah. Okay. That's the first one. And the second one, let's see the M1, 2. Alright, and then M2 is going to be equal to a reflection of some sort, I believe. So, is it? No, sorry, it is equals a stretch. No, it is a reflection. Oh no, this is a rotation. Wait. It's just a stretch with like a -1, like stretch parallel to the y-axis of stretch in the I think this is parallel to the y-axis with the x-axis fixed, scale factor -1. There's probably a different way to say that, but that's the only thing I can think of right now immediately off the top of my head for that. So yeah. So question B. Find the equation of the mirror line find the equation of the mirror line, so the invariant line of the reflection R represented by M3 equals M1 plus M2. Okay, so what this is saying is it wants us to work out M3 first, so M3 would equal M1 plus M2. Now this question doesn't say detailed reasoning, so you could just use your calculator for this. I'm just gonna multiply these all on my calculator. So 3/5 times 1. Okay, oh wait, no, I can just, this is actually quite easy. 3/5 times 1, and then minus 4/5 times 0. This could be 3/5, and then 3/5 times 0 and minus 4/5 times minus 1, so that's 4/5, and then 4/5 times 1 is 4/5, and then 3/5 times 0 is 0. 4/5 times 0, and this is minus 3/5. Right, okay. So that's M3, and then we've got that times x and y, or mx plus c, I should say. Mx plus c will equal x dash mx dash plus c. And then, so we need to now do this. So we want to do 3/5 x plus 4/5 mx plus c equals x dash, and then 4/5 x plus, minus 3/5 mx plus c equals mx dash plus c. This is going to get messy. I'm going to multiply both of these equations by 5 first. So 3x plus 4 mx plus c equals 5x dash, and then 4x minus 3 mx plus c equals 5 mx dash plus 5c. And then so we sub in 5x dash to get 4, I'm going to run out of space here, I'm not careful. 4x minus 3mx minus 3c equals 5, equals m times 3x plus 4 mx plus c plus 5c. So that's going to be equal to 3mx plus 4m squared x plus 4mc. So we have, and then I forgot my plus 5c, plus 5c. So we get, so let me just write this all. 4x minus 3mx minus 3c equals 3mx plus 4m squared x plus 4mc plus 5c. I'll rearrange this equation. So we want 4mx squared to be positive, to be honest, m squared x, sorry, to be positive, and then so we would get plus 6mx, plus 6mx, and then plus, and then we would want the other x term, maybe, minus 4x, and then plus 4mc plus 8c. And now we want to factorize our x. 4m squared plus 6m minus 4, and then we want to factorize out the c here, so let's do 4c m plus 2 and that will equal 0. That equals 0. So now we want now we need both of these to be 0 for it to be 0, and so let's solve this quadratic. Actually, I'm just going to put this in my solver. If my calculator would work, please, thank you. So 4, 6 minus 4 Yep, so that is going to be x and then 2x minus 1 and then x plus 2. Yep, and then that's going to be plus 4c n plus 2. So, oh wait, that is meant to be n's. Sorry, it's because I put in my calculator, I got confused there. N plus 2. So we have m equals minus 2 is going to be a solution. And then that's 4 plus 4c. And then c equals, well, c is going to be equal to anything. So we'd have y equals minus 2x plus c. And then we could also have c is 0 and m is 1/2. So y equals 1/2 x as well. However, I don't think that is meant to be right. This is the equation of the mirror line. I'm getting 2 lines here. Yeah, I'm not sure why I'm getting 2 different things. I feel like a mirror line. Does a mirror line have to go through the origin? I'm just gonna say mirror line because that's the only thing. Mirror line has to go through origin. Therefore, y equals 1/2 x. That's what I'm gonna say. I don't know if that's right, but I feel like that's what this one's. So 3 intersecting lines L1, L2, and L3 have equations like so. And they are the triangle of 3 lines. So we have this triangle here. So these are going to be our lines, and they're going to, like, you know, go through each other like so. We want the angle here, or like the angle here. Any of those angles really, but we can work that out using the dot product. Then we want, then what else do we want? We want the, okay, yeah, we want the modulus of this length here and the modulus of this length here, half AB sine C. So, okay, that should be doable. So we want this, work out this intersection. We want to work at the intersections of the lines and also the dot product of 2 of them. Let's just shrink this down a bit. Is this all the speed? Oh wait, I missed the question. Wait, bro, what am I doing? I missed the question. It is claimed that the reflection represented by the matrix M4 equals M2 M1 has the same mirror line. Explain whether or not this claim is correct. There's the same mirror line. So this is correct. So 1, 0. I mean, this is worth 3 marks, so maybe we could just multiply this out again. 3/5 minus 4/5, 4/5, 3/5. And this will be 3/5, 0, minus 4/5, 0, and then 0, wait, 3/5, 0, and then minus 4/5, 0, and then 0, and then minus 4/5, and then 0, minus 3/5. This does seem similar in some ways, but like the opposite, right? So like the same mirror line as what? You could probably use eigenvectors for this, but I can't think of a way to do this fast because there's no way it wants you to color the invariant lines again. Surely, because it's only 3 marks. I think I'm just going to argue that the transformations are not, and matrix multiplication is not commutative. Matrix multiplication is not commutative. So M1, M2 is not equal to M2, M1. And so what you're doing is you're rotating it and then stretching it. So transformations M4 and M3 are not equal. And so they would transform a vector differently, and so the claim is incorrect. So then we're going to do question 12. So question 12 is we have 3 lines. So we'd have like this, this, and this. Yeah, because it wants that area. So this would be like theta, right? And we can work out using the dot product. And then we would want the modulus of this length here and the modulus of this length. And then we can use a half AB sine C. So we want this point, this point, this point, and then yeah, we can calculate this. So we want to, yeah, this is 9 marks, which I guess makes sense because we're gonna have to do a lot of calculations here. So let's get all these lines into our parametric form. So that's going to be, the first one's just going to be R1 equals, or L1 I should say. L1 is going to be 0, 0, 0 apparently, plus lambda 2, 3, 1. And then L2 is going to be equal to, okay, 0, 0, 0. So all these start at the origin, right? No, not the last one, actually. 1, 2, minus 4. Then L3 is going to be equal to 1, 2, minus 4. And then plus, oh, this is T, let's call this, and then let's call this S, for example. S, 1, 1, 5. So, actually these two will intersect at the origin if we set lambda equals 0. So lambda equals 0, t equals 0, L2 equals L1. So this is 0, 0. Let's put it. We already have one of these intersections, which is nice. So if we're calling this like L1, this is L2, for example. We will find out the intersection of L2 and L3, so then we could say maybe 2 lambda equals 1 plus s, and then we'd have 3 lambda equals 2 plus s, and then we could solve this. Also, we need to check if they were consistent, I guess, but like, maybe. Sometimes they're pedantic about these things. If you don't check that they're consistent, then they can dot your marks, I guess. So minus 4 plus 5s, let's just put that in just in case. 5s, that looks dodgy. Maybe that's better, 5s. And so then we can just solve these two simultaneously. So lambda equals, s equals, s equals 2 lambda minus 1. So then we have 3 lambda equals 2 plus 2 lambda minus 1. 3 lambda is going to be equal to 1 plus 2 lambda. Lambda equals 1. And s will equal 2 minus 1, 1, right? So let's see this. So 1 plus 1 is 2. This equals 2, yeah. Oh yeah, okay. I probably could have just solved that and then showed they're consistent. Yeah, okay. I definitely could have just done that in my head, but oh well. It's fine. And then so we can then say that the L1 equals L2 at 2, 3, 1. And then so now we need to, L1 equals L3, sorry, 2, 3, 1. And then so we just need to find this point here. And then so we would just need to find, wait, so that was L1, that was L3. We found that point there, that's 2, 3, 1. I keep track of that, so we use the right angle, I guess. Like, it doesn't really matter that much which way you do this around, like this triangle, but you want to keep track of which points which and which lines which, so you can choose the right angle, I guess. So then L1, L2 and L3 will be, so we have t is equal to 1 plus s, and then we would have 2t is equal to 2 plus s, so then we would have 1 plus s, 2 plus 2s is equal to, wait, what am I doing? 2 plus 2s is equal to 2 plus s, so then s is equal to 0? Yeah, oh yeah, okay, no, that's, yeah, nice, okay, yeah, that makes sense actually. Okay, so s equals to 0. Yeah, I could have just seen that as well. Yeah, all these actually could get away with not doing any working out, which is kind of crazy for 9 marks. But yeah, so this is going to be 1, 2, 4. So now if we do 2. So now if we do, so we call this point like O, A, B. We need to do O, A dotted with, and then B, A. And so that is O to A is going to be 2, 3, 1 dotted with, and then that is a, wait, there should be a minus 4. And then so that dotted with B to A, which is 2, 1, sorry, 2 minus 1 is 1, 3 minus 2 is 1, and then 1 plus 4 is 5, and then over the square root of 2 squared plus 3 squared plus 1 times the square root of 1 plus 1 plus 25. So we're going to get 2 plus 3 plus 5 over Bro, this warning on my calculator, I need to replace the batteries. 2 squared plus 3 squared plus 1. Root 14 times, and then root 27. I'm just going to put that as, because obviously it is. Yep. Yeah, so then we're going to do that is equal to cos of theta. So theta, oh, we might need to bloody right angle triangle thing here. Okay, yeah, so we can say actually, yeah, okay, let's just do that. So 2 plus 3 plus 5, 2 plus 3 plus 5 is going to be 10. That's 10 over root 14 times root 27. 3 root 42. And then so we can, what we can do here is draw a right angle triangle. If that's theta, then adjacent over hypotenuse, that must be 10. That must be 3 root 42. So now we use Pythagoras. 3, so then we do 3 root 42 squared minus 10 squared gives us 278, and that squared, so root 278. So this is root 278. Just 278 plus 100 square root. Right? Yeah, okay, so that's root 278. So that means that sine of theta is equal to the opposite over the hypotenuse. So that's root 278 over 3 root 42. So then we can use a half AB sine theta equals a half times, well, we calculate, and this is oh, you know what we could have done? Oh, we literally could have used the cross product, actually. Yeah, literally could have used, yeah, you could have just crossed, actually. You could have crossed O to A. You could have O to A cross B to A. And that would have worked, because the magnitude of that is OA, BA, sine theta. So yeah, you could have done that. But I mean, this way, I mean, the cross products, yeah, actually, because you could have put on your calculator, that would have been well easier. But I guess there's 2 ways to do it then. I'm already in too deep into this method. So that would be root 14 times root 27 times root 278 over 3 root 42, which is going to give a half times root 14 times root 27 times root 278 over 3 root 42. So the area is 8.3372 for significant figures. There you go. So that's that question. This is probably the last question we'll do for this video, and then we'll probably end it off. So 13a, using logarithmic form of arcosh. Okay, so this is an easy 5 marks here. So y equals arcosh. You should just do this derivation and then just like write it down, right? So this is cosh of y equals, oh, this is using the logarithmic form. That's my bad. Yeah, okay. So much for talking all that. Okay, so look at the formula booklet. Our cosh is ln x plus the square root of x squared minus 1. Yeah, okay, x squared minus 1. ln x plus the square root of x squared minus 1. Okay, yeah, this is okay, because y. So so we want to use the chain rule here, so dy by dx is going to be equal to f prime of x over f of x. So where f of x equals x plus the square root of x squared minus 1. So that's going to give us f prime of x is going to equal 1 plus, and then if we do, so x squared minus 1 to the half plus x equals f of x. Well, f prime of x equals 1 plus a half times 2x, x squared minus 1 to the minus a half, which equals, that's meant to be an x, times 2x, so that's going to be 1 plus x, 1 plus 1 plus x over the square root of x squared minus 1. And then you go do that, 1 plus x over the square root of x squared minus 1 divided by f of x, which is x plus the square root of x squared minus 1. So, I guess we can do, put that all over one denominator, I guess, because that'll make this easier. So, x squared minus 1 to the half over x squared minus 1 to the half plus x times, and then flip that over, so 1 over, yeah, okay, x plus root x squared minus 1. How do we go to here? We use the common denominator. Just write that down in case I lose a mark there for not explaining that too thoroughly. And then to that and that cancel, and you get equal 1 over x squared minus 1 to the half. So yeah, the trick there was just to notice the common denominator here. Let me actually just write that as root x squared minus 1 over root x squared minus 1 plus x over root x squared minus 1 divided by x plus root x squared minus 1. Yeah. Okay, and then that extra step should show what I've done there. So, yeah. There we go. That's that. 13b, hence find the integral of this. Okay. Okay, yeah, so hence find the integral of 2, 1 arcosh of x dx. So we know that arcosh is an ln, and so the only way to integrate that is by integration by parts. However, we split into that ln form, it's probably going to get messy. So, and we just worked out the derivative of arcosh, haven't we? So yeah, we can just say let u equal arcosh of x and v equals 1, then, and dv equals 1, sorry, and then du equals 1 over root x squared minus 1, and v equals x. And as I said, the reason I'm going straight into parts is because this is a logarithmic. This is realistically just a disguised logarithmic integral, but you just don't want to don't want to split it into that ln, because, I mean, what then you'd have u equals ln of x plus the square root of x squared minus 1. And then you'd have to, you know what du is, but then, like, I guess you could use that. Because uv minus v du. Yeah, you could definitely use that actually, but yeah, you actually could, but I'm just gonna leave this arcosh because, well, it's just gonna make my life easier writing this out. So then it's gonna be uv, which is x arcosh. That's not your right arcosh, is it? Arcosh of x and minus the integral of v du. So that's just gonna be x over square root of x squared minus 1 dx. That's going to be 2, 1. That's going to be 2, 1. So now here's the bit that I'll probably end up making a mistake on, if I'm being honest. X, and then let's rewrite this as ln because we're going to need to sub it all in and it wants it in logarithmic form. So x ln x plus the square root of x squared minus 1. I'm not going to sub in just yet. And then minus the integral of, let's try and solve this integral. That's just a reverse chain rule, right? So x squared minus 1 to the half. If I just do x squared minus 1 to the half, try x squared minus 1 to the half equals a half times 2x x squared minus 1 to the minus a half. Yep, so it is literally exactly that. So then that's going to be x squared minus 1 to the half 2, 1. And then we want this to then graph this out basically. So I'm 2 ln of 2 plus square root of 4 minus 1, which is 3. Minus 1 is 1, so ln of 1 plus the square root of 1 minus 1, which is just ln of 1, right? Yeah, ln of 1, which is just 0. So that works out nicely, and then minus, and then we're going to keep that minus in for now because I'm not making sign errors this late into a question, hopefully. I don't want to, so 4 minus 1 is 3 to the half, minus, and then 1 minus 1 is 0, okay. So then that's 2 ln 2 plus root 3 minus root 3, and why I wrote a plus there, minus root 3. Is that an exact ln form? I mean logarithmic form, I feel like that's fine. There we go. I probably might have made a mistake there, but I'll get the math marks. Ali, hello, Ali. There's someone in my college called Ali, so that's kind of crazy, right? He's trying to evaluate the integral of 1, 0 arcosh dx using the calculator, and he gets error. That is not good, is it? It's not good. Explain why. Right. So you want cosh of x equals, well, cosh of x, okay, cosh of x has a minimum at y equals 1. It does not go lower. Therefore, cosh of x equals 0. Cosh of x is less than, cosh of x is less than 1, or so for cosh of x say equals 0, or r cosh of 0 equals x, is undefined. So when trying to do integral the bounds will not allow for an answer. The bounds are out of the range of arcosh of x for no area under the curve. Also, I guess you could say that, well, the x squared minus 1 to the half bit from 1 to 0 would equal, well, 0 minus 1 to the half, which is not defined. Therefore, error. Right, I think I'm going to leave this video there, and that's a good amount of ground covered in this video. We've got 1, 2, 3, 4 more questions left, and this chunky one at the end. I might make a completely separate video on that, just one video. Got some complex series here, another integral. This looks like another one of these hyperbolic ones, which is interesting. And you've got matrices, equations of planes, things going on there. That's quite interesting. But yeah, I hope this helped. Like, subscribe, and yeah, I'll see you in the next one. Goodbye.